Finally, let's take a look at this challenge problem, reach the prize in the maze. It states that we found ourselves in a maze, and the only way we can get out is to reach the prize, which will teleport us out of the maze. And it states that, assuming that we start at the first row and column, determine whether we can reach the prize. We're told that zeros represent passageways, and ones represent walls that we can't pass through. And we're also told that we can only travel up, down, left, and right. Our function escape maze, we're told, has one parameter, which is maze, and maze is a 2D list. If we take a look at the first sample case, we're told that for this maze, the sample output should be true because there is a path going from the starting point, which is the top left, to the prize, which is 2. And for the next case, we're told that our starting location is a wall, so we can't reach the 2, so our sample output should be false. So let's take a look at our first maze. We can see that for this maze, we start at the top left, and we can in fact reach the prize because we can take this path, which will enable us to reach the prize and get out of the maze. And we're told that for the next problem, or for the next sample case, because we started at a wall, we can't go anywhere, so this is false. Okay. So what do we know, and what do we know? We know that if our starting location, or if our current location is a wall, then we can't progress through the maze. What are some other things that we know? Well, something else that we also know is, before I even go there, the way that we're going to approach solving this problem is again using a technique called recursive backtracking. And this problem is a classic example of a problem that uses recursive backtracking in order to solve the problem. And recursive backtracking involves us using recursion to solve a greater problem by building a solution incrementally and using the solutions to those smaller problems to reach our bigger problem. So in this case, what we're going to do is we're going to recursively traverse our maze and see if, given our starting location, we can reach the finishing location. Alright, so how do we do that? Well, what we're going to need to consider for a recursive problem is a base case. We want to think about the base cases. Well, what are our base cases? I mentioned one of our base cases, which was if we're at a wall, then we're stuck. Well, what are some other possibilities? What if like we started at the top left and we were to try going to the left? Well, we know that would be actually out of bounds if we kind of imagine our maze like this. What if we were here is what I'm asking. Well, we would know that we would be in a valid row, but we wouldn't be in a valid column. The same thing applies if, let's say, we had traversed through this maze. We were at this point of the maze. What if we just said, let's just try going to the right? What if we want to be here? Well, we can't be there either because that is, well, we're not going to reach the prize if we go out of bounds. So we know that if we go out of bounds, then we're also going to be stuck. So if those are going to be our base cases, well, another base case we have actually that I forgot to mention is, what if we start at the prize? Well, that's a pretty trivial base case, right? So if we're at the prize, then we know that we can return true. Because what if we had a maze that was like this? Well, that wouldn't be much of a maze, right? I mean, you can just get out right away, but regardless, that is what the base case is. It's a trivial version of the problem. Okay, but what if we're at a 0? What if our current location is a 0? Do we know that we can get out of the maze? Not necessarily. So we need to try going either upwards. We need to try going up, to the left, to the right, and we also need to go down. Because if we look at the problem above again, let's see if I can do a little magic. Okay. If you take a look at the problem again, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 2. We know that, okay, so from this location, we're at 0. This is our current location. Let's try going up. Well, if we go up, we go out of bounds, right? So that's no good. What if we try going to the left? Well, that's also out of bounds, so that's not any good. What if we try going to the right? Well, if we try going to the right, then we hit a wall, so that's no good either, because we can't go through walls. So that our only option is going down. Well, so if we hit a wall, then what we can do is tentatively, we can return false and say, and just assume that if we hit a wall or if we go out of bounds, we're going to return false. We're going to say, there's no way to reach the prize if we take this current path that led me to reach this wall or led me to go out of bounds. That is all that returning false for these cases means. However, if we try going down from that starting location, remember the top left is our starting location. If we try going down, then we again hit another 0. And if these are our base cases and this is the else, remember, then we know that 0 is our current location. So we need to try the possibilities that we set right here. We can either go up, to the left, right, or down. Well, if this is our current location, and let's say we were to go back up, well, intuitively we know that we probably don't want to go back and visit places that we've already visited, right? So because if we were to go back up, like let's say we were to go back up. If we went back up, then we would be back at our starting location and we would be back at the 0. And based off of what we've said in our code, we state that if 0 is our current location, we try going up, left, right, and down. That means that we would go back, we'd be back at our starting location. We would try going up again. We know that that's out of bounds. We would try going to the left again. We also know that's out of bounds. And we try going to the right. We know that's a wall. And then we try going back down. And then it would just be this like infinite loop of us going up and down, up and down, up and down. And we would never get out. That's not what we want, right? So we want some sort of notion or some sort of way of keeping track of the places that we visited. The places we've visited. The places we've visited. So we need a way of keeping track of the places we visited. So what I'm going to do is I'm going to create, what we can do is we can create, let's say, an array of zeros that are equivalent in size of the maze. And what this is going to do is as we traverse our maze and we hit locations, we come upon indices in the maze, we mark them as visited so that we no longer have that problem where we go up or we go down and then we go back up, or there's another case where we might go to the left and then we go back to the right, or we go to the right and then we go back to the left, and so on and so forth. We basically don't want to be stuck in this maze forever because we keep banging our heads in a wall going back and forth, back and forth, back and forth. So what we can do is after we've considered the possibilities at this location, like we try going up, we try going to the left, we try going to the right, and we try going down, then we mark this node, or not this node, we mark this index as visited and we just say it's a 1. And then after we're done going to the left, to the right, and down of this one, we mark that one also as a 1. And in this way, we can actually, like, let's say we again mark this as a 1. This way we know that, let's say we try going back up. Well, if we try going back up, we don't want to try going to the right, to the left. We don't want to try going back up because we know we've already done that work. We don't want to do that again. So another thing that we can do is add another base case, and right here just say if we visited this location, then we can return false. We know that we've tried everything. There's no hope from taking this path. Alright, so we've covered everything that we actually need. So we can either go up, left, right, and down. We know that our base cases are if we're at a wall, we're stuck. Or if we go out of bounds, we're stuck. If our current index is 2, then we know we've reached the prize. But if the current place that we're at in a maze is a 0, then, or if it's a 0, I need to say if it's a 0 and it's not visited, because we just covered why we need to keep track. We need some notion of keeping track of where we visited. So if it's a 0 and it's not visited, then we need to try traversing the valid ways that we can go through the maze, which are again up, left, right, and down. Alright, so now let's try putting this into code. So the first thing that we want to do is, because this is a recursive backtracking problem, we're going to need some sort of helper function that will enable us to perform the recursion. So first thing is we're going to want to define a helper function which will take the maze, and we need some sort of notion of where are we in the maze currently. So we need to know what row are we at currently and what column are we at currently, right? Well, actually, we need one more thing right here. We need to keep track of the places that we visited. So we need to keep track of another 2D list, which is the same size as our maze, that keeps track of the places we visited. Okay, so what we're going to do in escape maze is we're going to create that visited 2D list. So what we're going to do is we're going to do some list comprehension. So 0 for j in range length of maze. And what this is going to do is it's going to create the 2D. Oops. There are a lot of there are a lot of brackets and parentheses that I'm keeping track of. I believe. Alright, so what this inner part is going to do, it's going to create the rows of zeros of the length of the maze, like of the length of a row in the maze. So maze 0 is one row, and so we're just going to create zeros. We're going to create a list of zeros that are equal to the length of a row in the maze. And then for I in range, length of the maze is going to say we're going to create that many rows of zeros for how many rows there are in the maze. Alright, and then we're going to pass that into our helper. So we're going to pass our maze, of course, because that's the thing that we're traversing. We're going to pass our visited array because we want to keep track of the places we visited so that we don't run into that problem where we go up and we go down and we go up and down and up and down. And we just kind of bang our heads into, just keep banging our heads because we keep going through the same locations. And we also want to pass 0 and 0 because we know that we start at the top left. Alright, great. So we know that our helper function needs to return a boolean because, as we're told here, the function is expected to return a boolean. So if this is returning the result from our helper function should return a boolean. Alright, so what do we remember about our base cases? What we remember is we know that if we're at a wall, we're stuck. If we're out of bounds, we're also stuck. Let's do the case of if we're out of bounds. So how do we know if we're out of bounds? We know that we're out of bounds if, let's say, our row is less than 0. What does that mean? If our row is less than 0, let me just clean this up really quickly. Delete. Great. We know that, let me just really quickly do this again. If we're at, if our row is 0, so if our row is less than 0, then that means that we're somewhere here. We're either here, 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 and so forth, because remember, this is row 0, this is row 1, this is row 2. So if our current row that we're at is less than 0, then that means we're out of bounds. If our current column is less than 0, that means we're here somewhere. That's no good also. So we know that. Oops. Let's bring that back. If our current row is less than 0, or if our current column is less than 0, well, what if our row is equal to the length of the maze? If we remember, the length of the maze, so the length of the maze is equal to the number of rows in the maze. Well, the number of rows in the maze is 3, right? We can see 1, 2, 3, but we know that our rows are 0 index space. So this is row 0, this is row 1, this is row 2. So if the current row that we're at is equal to the length of the maze, then what does that mean? That means that we're somewhere here. That means that we're also out of bounds. And the same thing can be applied for if we're at length of the maze 0, right? Because that would mean that we're at here in the maze. We're again out of bounds. So let's take care of that as well. Or if our row is the length of the maze, or if our call is equal to the length of the maze of 0, then we return false. What else do we know? We know that if we remember our base cases, what if we're at a wall? We know that we're stuck. Let's return false. So if the current place that we're at in the maze is equal to 1, return false. What else do we know? We also know that what if the place that we're at in the maze we've already visited? Well, we know that if the place that we're at the maze is already visited and we're still trying to traverse the maze, then that means that if we were to go back to the place that we visited, we wouldn't find a new path that would lead us to the prize. Like, there would be no point of us going back up, back to the left, back to the right, or going down. There would just be no point. So we know that we can return false. What if the place that we're at in the maze is 2 though? Well, that would mean that we've reached the prize, right? Like, we want to be at 2. So if the current place that we're at, if maze of row and call is 2, then we want to return true. What does this mean? If we're inside this else statement, that means that our current place in the maze is not a wall, because this is a wall. We visited this place already. And this would mean that we've reached the prize. So if we're in this else statement, that means that we haven't visited this location yet, but we haven't visited the location yet, and we haven't reached the we haven't reached the prize either. But we can still traverse and determine. We can still traverse the maze and determine whether we can reach the prize. The first thing that we want to do is we want to make sure that we mark the place that we're at right now as visited, because again, we don't want to run into any problems where we keep going back up, back down, back up, back down, because that would result in something called Stack Overflow, which I'm sure you guys have seen already. So we want to make sure that we denote that the current place that we're at is visited. Then what we want to do is we want to return the result of us going either up, to the left, going down, or to the right. Because what we want to do is we want to try every possibility. We want to kind of make our way around the maze and, like I said, try every possibility. So we want to return helper maze visited. And what do we want to put here? Let's say we want to go let's say we want to go up first. Row -1 would be us going up, or because we want to do or instead of and, because we can't reach the prize by going upwards doesn't mean we can't reach the prize at all, right? We just need a way of reaching the prize. So or helper maze visited row +1 call, or helper maze visited row call call -1. This would be us going to the left. This would be us going down, or helper maze visited row call +1. That would be us going to the right. So what have we covered? We've covered our base cases, which are if we're out of bounds. This is if we're out of bounds. If we are out of bounds, return false. There's no hope here. If we're at a wall, return false. We can't reach the prize. We're stuck. If we've already visited this location, there's no hope. We've already tried going up, left, right, and down, and we haven't been able to reach the prize. There's no point in us doing that again. So we're going to return false. We've reached the prize. The current path that we took, whichever path we took to get to this location in the maze, row call, we eventually reached the prize, so we want to return true. Otherwise, we haven't visited this location yet, but we haven't gotten to the prize yet either. We can still traverse the maze and determine whether we can reach the prize. But we want to prevent us from visiting this location multiple times, so we mark this place as visited, and we return the result of us trying every single possibility. We try going up, we try going down, we try going to the left, and we try going to the right. And if we try running this code, we can see that our output is true and it matches our expected output. We can in fact get out of that first maze, and we can see that all of our test cases have passed. So we can submit our code and we're done with the test.